Welcome to this crash course on chemistry. Let's get started. Let's begin with some basic definitions. Matter has mass and takes up space. Elements, like hydrogen, are composed of one kind of atom, while compounds, like H2O, are composed of two or more elements in a fixed ratio. Matter can be classified into mixtures and pure substances, and the three main states of matter are solid, liquid, and gas. Solids have a definite shape and volume, and cannot move as much as liquid or gaseous atoms. Liquids can take up the shape of their container and have a density in between that of gases and solids. Gases consist of a large number of tiny, quickly moving particles that are spread out, and thus have a low density and undefined shape and volume. Two types of changes are physical changes, which often convert the state of a substance, and chemical changes, or chemical reactions, which change the identity of a substance entirely. The periodic table of elements consists of unique elements, where elements with similar chemical properties are in the same column. Elements that are metals tend to be shiny, malleable, and conduct electricity well, and nonmetals tend to be brittle, poor conductors. Metalloids are semiconductors in between nonmetals and metals, and noble gases are generally unreactive. When scientists take measurements, the gold standard is the SI system of measurement, consisting of 7 base units: meters for length, kilograms for mass, seconds for time, Kelvin for temperature, moles for amounts of substance, amperes for electric current, and candelas for luminous intensity. To convert from an SI unit to another unit, we use conversion factors such as 1 meter equals 3.28 feet. Weight is a measure of the gravitational pull on matter, and density is a ratio of mass to volume. Accuracy is how close a measurement is to a target value, while precision is how close a set of measurements are to each other. The percentage error is found by subtracting the measured value from the target value, dividing by the target value, and then multiplying by 100. Significant figures, or sig figs, consist of the known digits of a measurement plus one final digit, which is uncertain. Mass and energy cannot be created or destroyed in chemical reactions. They can only change forms. Atoms consist of a nucleus surrounded by a cloud of negatively charged electrons. Inside the nucleus are protons with a +1 positive charge and neutrons with no charge. Electrons have a charge of -1. Additionally, neutrons and protons have pretty much the same mass at over 1,800 times the mass of electrons. The atomic number of an element is the number of protons in an atom of the element, and the mass number is the number of protons plus the number of neutrons. Isotopes are elements with a different number of neutrons, and the average atomic mass of an element is the weighted average of all the naturally occurring isotopes of an element. Avogadro's number is approximately 6.02 times 10 to the 23rd, where a sample containing a number of particles equal to Avogadro's number contains a mole of those particles. We can use Avogadro's number to convert from moles to particles. Quantum theory states that electrons can only exist at certain atomic energy levels. When electrons move to higher energy levels, they absorb energy, and when they fall to lower energy levels, they release energy in the form of photons or light. Light has a dual wave-particle nature. In other words, it can act as a wave and as a particle. The Heisenberg uncertainty principle states that we can either know the position or the velocity of an electron, but not both simultaneously. An orbital is a 3D space around the nucleus of an atom, which shows the region where an electron is most likely to be found. The columns in the periodic table are called groups, and the rows are called periods. We can use the periodic table to see certain trends, such as electronegativity, or the strength which an element pulls electrons towards itself, and atomic radius, or the radius of an atom. The outermost electrons in an atom are called the valence electrons. These can be found by looking across the rows of the periodic table, which can be divided into the S, P, D, and F blocks. For example, carbon has 2 electrons in the S block and 2 electrons in the P block, so it has 4 valence electrons. Atoms with a full valence shell of 8 valence electrons, such as the noble gases, are said to have an octet. Atomic bonds, also known as intramolecular forces, typically consist of covalent bonds and ionic bonds. Covalent bonds tend to be between nonmetal atoms, where the two atoms share one or more pair of electrons. Ionic bonds tend to be between metal atoms, where a positively charged ion bonds with a negatively charged ion. Positive ions, or cations, are atoms which have lost one or more electrons. Negative ions, or anions, are atoms which have gained one or more electrons. Once atoms bond, they form molecules, and to predict the shape of these molecules, we can use Vesper theory. Here is the Vesper chart, where the steric number refers to the number of bonds and lone pairs, and lone pairs refer to unbonded valence electron pairs in atoms. Some forces between molecules, or intermolecular forces, are dipole-dipole forces like hydrogen bonding, and London dispersion forces. Shown is a quick guide to naming compounds, where polyatomic just refers to a molecule which consists of different types of atoms. To know whether a chemical reaction is taking place, we can look for clues like heat, light, or gas being released, a color change, or the formation of a precipitate, or leftover solid substance. There are many different types of chemical reactions, such as synthesis reactions, decomposition reactions, single displacement reactions, double displacement reactions, and combustion reactions, and shown are examples of each. These equations have to be balanced, where the total number of atoms of each element is the same on each side of the equation. So for example, if you started with 6 oxygen atoms in the reactant side, you need to end up with 6 oxygen atoms in the product side. The gas laws are Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, and the ideal gas law. Boyle's law shows that volume and pressure of gases are inversely related. Charles' law shows that volume and temperature are directly related. Gay-Lussac's law shows that pressure and temperature are also directly related. The combined gas law and ideal gas law are simply a combination of these 3 laws, and the equations for all these laws are shown. Solubility is a measure of how much solute can dissolve in a solvent, where changes in pressure and temperature can increase or decrease solubility depending on whether the solute is solid, liquid, or gas. Molarity is the ratio of moles of solute to the liters of solution, where molality is the ratio of moles of solute to kilograms of solvent. Formation of ions when an ionic solid dissolves is called dissociation, and formation of ions from a molecular compound is called ionization. Colligative properties like boiling point elevation, or increase in boiling point, and freezing point depression, or decrease in freezing point, depend on the total number of solute particles present. Acids have a sour taste, while bases have a bitter taste. Acids are proton donors, and bases are proton acceptors, where a proton is a hydrogen ion. Additionally, acids are electron pair acceptors, while bases are electron pair donors. Strong acids dissociate more strongly in solution than weak acids and form weak conjugate bases. Weak acids dissolve more weakly and form strong conjugate bases. Acids have a pH of less than 7, bases have a pH of more than 7, and neutral solutions have a pH of 7. pH is a negative log of the concentration of protons, while pOH is a negative log of the concentration of OH- or hydroxide ions. pH plus pOH equals 14. pH can be measured using a pH meter or acid-base indicators. Additionally, titrations use a solution of known concentration to determine the concentration of a solution of unknown concentration. Reactions tend to proceed from high energy to low energy. If energy is decreased, the reaction is called spontaneous, and if energy increases, the reaction is not spontaneous. Entropy is a measure of the randomness of a system. Life decreases entropy on Earth while increasing the entropy of the rest of the universe. The enthalpy change of a reaction is the amount of energy absorbed as heat by a system at a constant pressure. A reaction mechanism consists of the steps of a reaction, where a reaction occurs only if the particles of the reactants collide. The activation energy is the energy needed to merge valence electrons and loosen bonds enough for a molecule to react. The rate of a reaction depends on many factors, such as concentration and nature of the reactants, temperature, and the presence of catalysts, which speed up reactions. Forward reactions are when reactants turn into products, and reverse reactions are when products turn back into the original reactants. When there is no net change in a system, In other words, when the forward and reverse reactions occur simultaneously and at the same rate, the system is in equilibrium. Le Chatelier's principle states that when a change in concentration, pressure, or temperature is applied to a system in equilibrium, the equilibrium shifts in the direction that relieves that stress. For example, increasing the concentration of the reactants would lead to a shift from the reactants to the products as more products are created from the reactants. The oxidation number is based on the distribution of electrons in a molecule. See the following table for a set of rules by which oxidation numbers are assigned. Oxidation-reduction reactions, or redox reactions, consist of two half reactions that occur simultaneously. Oxidation involves the loss of electrons, where a species whose oxidation number increases is oxidized. This species is also called the reducing agent, since it gives electrons to the substance that's reduced. Reduction involves a gain of electrons, where a species whose oxidation number decreases is reduced. This species is also called the oxidizing agent, since it takes electrons from the substance that's oxidized. The oxidation-reduction reaction must be balanced, where the number of electrons lost in the oxidation reaction is equal to the number of electrons gained in the reduction reaction. In an electrochemical cell, oxidation occurs at the anode, or negative electrode, and reduction occurs at the cathode, or positive electrode. The cell consists of a wire connecting the electrodes and a salt bridge, where the cell is in a solution. The electrons travel through the wire from anode to cathode, and the ions flow through the salt bridge from cathode to anode. An electrochemical cell, called a voltaic cell, uses this movement of electrons to generate electricity. An example is a battery. Electrolytic cells, on the other hand, require energy to drive non-spontaneous redox reactions. An example is the electrolysis of water, where water is broken down into hydrogen and oxygen. The different types of radioactive decay are alpha emissions, beta emissions, positron emissions, gamma emissions, and electron capture. The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to decay. Nuclear fission and nuclear fusion are nuclear reactions where nuclei are split and fused to produce more stable nuclei and release massive amounts of energy. This is the focus of the field of nuclear chemistry. Other fascinating fields include organic chemistry, the study of the molecules of life, and biological chemistry, the study of the chemical processes in living organisms. And that's it. Thanks for watching, and I hope you found this video helpful.